Hello again, Physics 30s. In today's lesson, we are most likely going to review a few atomic models that you either discussed back in Science 10 or possibly in Chemistry 30, although this time around we're really going to focus on why these atomic models fail. And in fact, to explain the failure of one of the models, we're going to have to relate it to Maxwell's principle of electromagnetism, which we talked about in the previous lesson. Our learning outcomes are to 1. Explain how the discovery of cathode rays contributed to the development of atomic models. 2. Explain qualitatively the significance of the results of Rutherford's scattering experiment in terms of scientists' understanding of the relative size and mass of the nucleus and the atom. And 3. Explain qualitatively how emission of EMR by an accelerating charged particle invalidates the classical model of the atom. Okay, let's start with one of the earliest atomic models, that from John Dalton. I think sometimes the description used for this model is the billiard ball model. And what this model tells you is that if you take an object and you break it down into the smallest possible building blocks that you can, all elements are made up of small particles. They're called atoms, and you cannot break an atom down into anything smaller. Hence the word indivisible. It's not possible to break an atom down. Which tells us that, yes, the atom is the smallest building block or the smallest possible particle. However, later on, our man, J.J. Thomson, comes along and he performs a cathode ray tube experiment. This was discussed back in the unit on magnetic forces and fields, where he took a cathode ray and subjected it to a combination of magnetic and electric fields. And there were essentially two really important things that were two important results from that experiment. The one result showed us that the cathode rays are made up of electrons. The significance of this is that an electron is subatomic, which immediately invalidates the Dalton experiment, or not the experiment, the Dalton model, because the Dalton model says that you can't break an atom apart. But we know an electron is something within an actual atom. The other thing of significance from this experiment was that it allowed us to calculate the charge to mass ratio of an electron. However, we're not going to worry about this one so much right now. We're going to worry mainly just about the electron being a subatomic particle. And indeed, that's what his cathode ray tube, or CRT, experiment proved. It showed that there are these subatomic particles that are called electrons, and that the Dalton model is, in fact, incorrect. Thomson's model, and there's a couple of phrases or descriptions of his atomic model. I think one is called the billiard ball model, or we have the raisin bun model. We have in the raisin bun model is the atom is a sphere of positive charge. You can kind of think of it, I suppose, like this green area as being this sphere of gaseous positive charge. Within this sphere of gaseous positive charge, you have an equal number of electrons. So I believe if you want to make reference to the raisin bun model, the electrons would be the raisins, and the sphere of gaseous positive charge would equate to the bun. Because you have an equal number of positive charge and electrons, and I don't believe at this point they were calling positive charges protons. We'll get into that in a moment. Overall, the atom is electrically neutral. So again, it's showing what So again, Dalton would have said that this outer sphere was as small as you can get. And due to Thomson's cathode ray experiment, we can now say there are smaller subatomic particles that do make it up. And you know what? Like, even though we know this is not like the most accurate model, it does for the most part explain principles of electrostatics. When I say electrostatics, I just mean, like, for example, if you like contact a positively charged object with a negatively one, and you want to look at the transfer of electrons from one object to another one, the Raisin-Bunn model is sufficient in doing this. The other thing I wanted to point out with the Raisin-Bunn model is that when you look at it, the distribution of the positive and negative charges is even. Charge density is even. So there isn't an area in the actual atom where the charge is all clumped up. It has a nice even distribution all throughout the atom. We now get into Rutherford's experiment. Again, this is quite a bit later on. So we have 1911 now. And he performs what is referred to as the scattering experiment. And let's look at this. Okay, so I'll try to explain what's going on just piece by piece. Okay, so over here, I have a lead box, and this lead box has a small little hole just on one side of the box. And inside of the lead box, we have a small sample of uranium. Now, we're going to talk more about this in the last unit of study, but uranium is radioactive. And specifically, it's radioactive and undergoes a type of radioactive decay, which we'll later learn about, and it's called alpha decay. Which basically means the uranium atom is not stable, and over time, it starts to emit alpha particles. So alpha decay just involves the emission of alpha particles. So these little green dots that we see, we would be emitting alpha particles in every single direction, but what we're doing is we're just going to allow the alpha particles to pass through one hole. The importance of using lead is lead has a thickness that is good enough to actually absorb alpha particles. So I suppose it's a safe way of containing the alpha particles you do not want to actually leave this box. Now we're going to take those alpha particles, alpha 2 plus, and we're going to fire it at a very, very thin sheet of gold foil. So this thin sheet of gold foil is going to be located a little bit over here. The reason we use gold is because we can make a gold sheet extremely thin. In fact, and I have a hard time believing this, and I don't even know where I got this fact from, but you can I think, pound a piece of gold foil down to where it's only a few atoms thick. So it's extremely thin. This is important because what we're going to do is we're going to fire alpha particles at this gold foil, and we want them to pass through. If the gold foil was like really, really thick, there's absolutely no chance those alpha particles are going to go through. And then what happens is the alpha particles hit this gold foil, they interact with the gold atoms. So we're going to be concerned with like the structure of the gold atoms within the gold foil. And then they deflect and they hit a screen that's located over here. I believe the screen would be a phosphorescent light source, which means that if a high energy particle hits it, it causes the screen to glow. And I think that's why the screen is coated with zinc sulfide. And then I believe if you use a microscope, you can observe like where on the screen the alpha particles are actually going to strike. Okay, so that's the apparatus of the experiment. Now let's look at the expected results and the actual results. So according to the Thomson model, so if we fire alpha particles through a gold atom, let's go back to like what the gold atom would look like. So the gold atom would be this atom that's right here. This atom where I have a nice even distribution of electrons throughout this gaseous sphere. So we're going to fire alpha particles through that. The prediction is that most of these guys should just go through the gold atom undeflected. The reason they go through undeflected is because of the uniform charge distribution. So that there's not really any charge that's kind of like bunched up in an area. So for the most part, the particles can go through. I suppose you could think of it as like having like trying to like walk through like a really, really dense forest compared to like a forest that has like a much more uniform density. If like the trees are like more uniformly distributed, there's a bit more space between them, then if you walk straight on at that forest, it's pretty likely that you should be able to walk through without any problems. But if the trees are much more densely packed, then you're probably not going to be able to make your way through without like some kind of alteration to your trajectory. However, so we'd also predict, according to Thomson's model, that if any of these alpha particles get close to an electron, they're going to be slightly deflected. So if you draw one of the alpha particles, and I'll go to red. So say we have one alpha particle that came, that is not an alpha, that's a 2. Let's try that again. Alpha 2 plus. Okay, so this alpha particle would be attracted to this electron. So because it's attracted to that electron, its trajectory is just going to get slightly altered where it's going to curve up just a little bit. It's not going to curve up drastically because you have to think about this. These alpha particles have like a lot of momentum, and that electrostatic force is not enough to like significantly overcome the inertia of the alpha particle. So the alpha particle just wants to keep moving in a straight line, and the electrostatic force has a small influence, but not a huge one. So we do expect there to be some small deflections due to the electrostatic force, but nothing more than that. All right, so what actually happened? So most of these go through undeflected. And when I say most of them go through undeflected, I'm talking about like 99% plus of them go through undeflected. There's no issue. Many of them, there's some slight deflection. Okay, like maybe like a slight deflection would be like 0.1 or 0.9% of them have a slight deflection. Not a problem, okay, because we expect there to be slight deflection due to that electrostatic force. However, there's a few of them that actually, not only did they get deflected, they actually get reflected. They get sent back. Now, there are barely any that do this. Okay, like maybe like 0.0000001% of them actually get reflected back. I might be doing a slight exaggeration, but there are very few of them that actually do get reflected back at this huge angle. In fact, if we fired the alpha particles at the gold screen, so this is AU, so initially, most of them should just go through undeflected, no problem. Some of them, we got the slight deflection. If we start to expand this, pull the screen out, then we start to notice we're getting some pretty big angles. And in fact, if we pull the screen all the way around, we're noticing that they start to bounce back. If we go back here, there is no way that this can happen. Even if you had an alpha particle, oh my goodness, I did a 2 again. Okay, so I'm thinking of the 2 plus. That's why I'm doing the 2 first instead of the alpha symbol. Okay, so even if we had an alpha particle, there we go, approach one of these guys head on, I would say that like because this guy has such huge momentum, it would just plaster the electron and just move it out of the way. And it would still just go through either undeflected or maybe a small deflection. Okay, there's no way it's going to hit an electron and bounce completely back. So there's no way that this model can be correct because it can't account for this 0.00001% of my alpha particles that are bouncing back. So this is where the Thomson model fails. It cannot explain these major deflections. Okay, so let's look at Rutherford's model, which does explain why there are these deflections. The main issue with the Thomson model is that it assumes that the charge distribution is uniform. In Rutherford's planetary model, this is not the case. What we have is most of the mass and all of the positive charge is clumped together. And it's clumped together in the center of the atom that we call the nucleus. So instead of like all the positive charges being evenly distributed, they're all kind of jammed into like this one small region. That's called the nucleus. I want to point out at this point here that even though we know that the nucleus does also have neutrons in it, this was not something they knew at the time. I believe it wasn't until the 1930s that they were able to show that the nucleus also did contain neutrons, but for the time being, it only contains positive charge, your protons. Most of the atom is just nothing. There's empty space. However, in the empty space around the nucleus, we have some electrons that are orbiting. And we'd have an equal number of electrons to offset the number of positive charge. Okay, so how does this model explain the Rutherford, how does it explain the observations of the scattering experiment? Well, again, 99% of them just go straight through undeflected. That's because most of the atom is just empty space. So most of the alpha particles would just go directly through this space here. Nothing happens. Some of them will get slightly deflected. So if you have an electron here and an alpha particle comes close to it, okay, this is very unlikely, but let's say it does come close to it, then it would get slightly deflected. Or if the alpha particle came close to the nucleus, same thing. There would be like some slight deflection where maybe it would just go up a little bit right here. So why is it that in 0.00001% of the time I get these major deflections? Well, you need to understand how small the nucleus is and compare to the actual size of the atom. I think one good of an analogy of thinking about this is that pretend like a classroom is the size of an atom. The size of the nucleus would be like you took a single grain of sand in that classroom, and the size of that single grain of sand in comparison to the size of the entire room would be how big the nucleus would be. So you can imagine how difficult it would be to actually hit one of those tiny little grains of sand. And that's why only 0.0000001% of the time do I actually get the major deflections back. So what would happen in those situations is an alpha particle would approach head on. Now, it's not going to actually hit it. What's going to happen is because this guy has a bunch of positive charge, you're going to have an electrostatic force that gets really big. Again, think about Coulomb's law. So Coulomb's law is Fe is equal to K Q1 Q2 over R squared. So what we know is that there is an inverse relationship between distance and Fe, which means as the alpha particle gets closer and closer to the positive nucleus, this electrostatic force gets enormous. And it gets enormous to the point where it'll actually repel the alpha particle before it hits. So it never actually hits. It's just the major repulsive force that causes it to bounce back. And it does it so few times because the nucleus makes up such a small volume of the atom. Because it makes up such a small volume of the atom, very few of the alpha particles are repelled backwards. So again, it's important just to note that in this atom, there is not the uniform charge distribution like there is in the Raisin-Bunn model. all of our positive charges is kind of chunked together in this extremely small volume. I think when most people think of what the atom looks like, they try to visualize this particular model, but it turns out that this particular model also fails. And now here's where we're going to link this up with the previous lesson when we talked about James Clerk Maxwell's principle of electromagnetism. Okay, so let's set this up. Yes, the failure of this model can be explained by Maxwell's principle of electromagnetism. Okay, so let's say we have our dense nucleus. It's like a bunch of positive charges in here. And, you know, I'm just going to do one positive charge to make it simple. Okay, one positive charge. Here's my circular orbit. And here's my electron that is in that orbit. Now, because the electron is negative and the nucleus is positive, if you drew a free body diagram of the electron, there would be an electric force, an electrostatic force, that would point towards the center of the nucleus. There would also be a gravitational force, but as we've seen in a previous assignment, the gravitational force between an electron and a proton is completely insignificant compared to the electrostatic force. Okay, so we have an electrostatic force that would act on the electron, and this is a centripetal force. This would be like sigma Fc. It's a net force. Now, according to Newton's second law of motion, if we have a net force in a particular direction, we also have to have acceleration in that same direction. So if we drew a mass acceleration diagram of this electron, we would just have the direction of my centripetal acceleration, AC, that's also towards the center of the nucleus. Good so far? We have an electrostatic force that is my centripetal force, and if I have a net centripetal force, I have acceleration. Now, here's where we have a problem. According to Maxwell's principle of electromagnetism, what is the source of all electromagnetic radiation? Well, the source of all electromagnetic radiation is an accelerating charge. So this electron would actually be emitting an electromagnetic wave. So in your electromagnetic wave, I'll just draw like one of them. So you have like your oscillating electric field, which might look something like this. And then perpendicular to that electric field, you have that oscillating magnetic field. So maybe the magnetic field looks something like this here. So it's like really hard to draw a three-dimensional picture. Okay, we got our perpendicular magnetic field. We have the question, well, what is an electromagnetic wave? Or what's a wave in general? A wave is an energy carrier. So what's happening here? Well, if the electron's accelerating and accelerating charges emit EMR, they are basically emitting energy. They're giving off energy in the form of an electromagnetic wave. So what's that going to do? Well, if this guy's giving off energy in the form of an electromagnetic wave, the energy of the electron is going to decrease. Its kinetic energy decreases because it's giving off energy in the form of an electromagnetic wave. If my kinetic energy decreases, so does my speed. In order to maintain a constant orbit, you need to maintain a specific speed. So if your kinetic energy drops and your speed drops, you can't maintain that orbit anymore. And then what would happen? Well, if it can't maintain the orbit, then this electron is actually going to spiral into the nucleus, and then it's going to explode. Now, we know that this is not the case because we exist. If this model of the atom was actually correct, then there would be no atoms because every atom would just simply explode. So this cannot possibly be the correct model of the atom according to Maxwell's principle of electromagnetism. So the result of this is this loss of speed causes the electron to, and again, it's continuously emitting EMR, because even when it's spiraling, it's still accelerating. It has centripetal acceleration, and then it just keeps giving off more and more EMR. So eventually it's going to keep losing speed, will lose its kinetic energy, lose speed, spirals into that nucleus, and then it explodes. So this model is also insufficient. We're eventually going to get into the next model of the atom, dealing with the Bohr model. However, we need to set up a bunch of other things beforehand before we can approach that one correctly. So we'll come back to the Bohr model of the atom later on in the unit. In the meantime, you can complete the assignment called Early Atomic Models. And then in the next lesson, we're really going to talk about the true transition from what we call classical physics into what has been established as modern physics. And we introduce something called a photon. And I will talk to you in that lesson.